Bismillahirrahmanirrahim. So today's topic is on dimensional modeling. So we start with the need for dimensional modeling. That why the dimensional modeling uh, was required. So there were problems with early Kabolian data processing systems. These were the early systems in, you can say, 1980s. So there were lots of problem with those systems, and the big problem was data redundancy. So then to resolve this problem, uh, from flat file to table, it is decided to uh, translate each entity in the real world to a table in the physical schema. So we start making entities, identifying entities, and then each entity will be translated to a table in the physical schema. But when want to get answer from that schema, from those tables, usually it requires join, and a simple join has, you can say, complexity or cost of order n square, so which is a a large complexity. So why ER modeling has been so successful? But ER modeling is coupled with normalization, and it resolves the problem of redundancy, and it drives out redundancy out of the database. So and now, as the redundancy is removed, now you have two advantages, that you have to change, add or delete at just one place instead of multiple places. So this is a big advantage which results in success of OLTP systems. And it is used with indexing for fast retrieval of information. And as a result, there is success of OLTP systems. So, but the question is, if ER modeling coupled with normalization is so successful, uh, then why need for dimensional modeling? So this is the question. There are some observations regarding ER data model. That ER model, uh, in ER model, all tables look alike. All tables look similar. As a consequence, it is difficult to identify which table is more important. By just looking at the schema, you will be unable to answer that which table is the most important. Which table is largest in terms of number of rows? Which table contain numeric measurements, or in other words, facts about the business? And which table contain descriptive attributes, um, which make some hierarchy, like customer, product, time, location? These are descriptive or hierarchical attributes that basically describe the numerical measurements. So if you just look the ER schema, ER model, uh, you will be unable to answer these questions, and these questions are important in the context of decision support systems. So having a close look at this diagram, it reveals that a separate table has been maintained to store different entities, which results in a complex overall model. Now, probing the model to get information insight about data is not straightforward now. For example, we cannot tell by looking at the model the relative importance of tables, that which table is most important. We cannot know the table sizes, and most importantly, we cannot tell about business dimensions by just looking at the table headers. that which table contains numerical measurements, business measurements, and which table contain the static descriptive attributes, or you can say dimensions. So these are, you can say, drawbacks of ER modeling in the context of decision support environment. The need for dimensional modeling, complexity of representation for of ER diagram. So these two, you can say, graphs represent the same problem, but by just looking towards these graphs, you can't tell exactly that this represents the same problem, because they both are designed by different people. So many topologies for the same ER diagram all appearing different. So if you rotate any of the diagram, the entire representation will become changed. So very hard to visualize and remember a large number of possible connections to any two or more tables. And this is complex because there are large number of possible connections to two or more tables. So even for a simple retail, there can be dozens of tables in this ER diagram, because by default, ER diagram represents each entity of your business. And if you are making ER model for an enterprise, you can have hundreds or thousands of logical entities. That makes the ER diagram more complex. So need for dimensional modeling, ER and normalization, this we discussed in the previous slide as well, result in large number of tables which are hard to understand and hard to navigate. For example, you have to get answer of a query, you have to span or navigate multiple tables. So real value of ER is in using tables individually or in pairs. So too complex for queries that span multiple tables with a large number of records. So if you have to span large number of if a table has large number of records and your query has to span multiple tables, then ER modeling becomes very complex. So the difference between ER and dimensional modeling. So ER models are constituted to remove redundancy from the data model, facilitate retrieval of individual records. Thus, they are optimized for online transactional processing performance. Basically, it models the micro relationship among data elements that by default it mentions or models the detailed relationship, and avoid variability of the structure of ER models. That uh, if you ask two designers to make ER model for the same system, there will be variable, their structure of the ER model will vary. So by just looking towards the model, you can't say, you can't tell that these models represent the same problem. And very vulnerable to changes in the user querying habits because the schemas are asymmetric. And if there is any change in the business, then there can be a huge change in the schema also. Maybe some entities are included in the ER model, and the relationship with existing tables are also included in that. So this schema, in short, this schema is vulnerable to change if the business changes. Now talk about dimensional modeling. So it is constituted to optimize uh, decision support query performance. So this schema is optimized for decision support query performance, and it models the macro relationship. So it models the, you can say, macro relationship. It gives the bigger picture, overall picture. So all dimensions serve as equal entry point to the fact table. There are only two types of table in this dimensional model. One is the fact table, and another is dimension table. And there is only one kind of relationship between these two tables, fact table and dimension tables. So navigation becomes easy. Changes in user queuing habits can be accommodated by automatic SQL generators. So this schema is very less vulnerable to change if a change in business occurs. Uh, because there are only two kinds of tables in this schema, and having only one type of relationship between the tables. So if a business change, uh, uh, that change can be accommodated by automatics, and you want to generate a SQL against some query, so it will be easy with this schema. So how to simplify ER data model? We have already discussed a way to simplify ER data model, that is denormalization, which reduces the number of tables, in fact, in short. Now we are discussing another method to simplify ER model, that is dimension model. So what is dimension model? It is a simpler logical model that is optimized for decision support. So it is dimension in nature with a single central fact table and a set of smaller dimension tables around the fact table. It is designed, this modeling technique is designed to read, summarize, analyze numerical information, because we are concerned with numerical information, facts about the business when it comes to analysis, like values, balances, counts, weights, profit, margin, in etc. in a data warehouse. So it arranges data in such a way that it is easier to retrieve information and generate reports, because we are not concerned with updation in this case, or fast updation in this case, as we are concerned in OLTP systems. But here we are concerned with fast retrieval and uh, report generation. So every dimension model is composed of one central table with a multi-part key. And this central table is called fact table. And a set of smaller tables surround it, which we call dimension tables. So elements of dimension model. First is fact. So what is fact? Facts are measurements, metrics, or facts from your business process. Example of facts are this: the number of products, value of price, cost, profit, average. Dimension provides the context surrounding a business process event. In a simpler terms, they give who, what, where of a fact. Basically, through dimensions, you get the meaning of the fact. Without dimensions, the facts are meaningless. So dimensions are a window to read the facts. So basically dimensions are the hierarchical attributes. So window to view information in the facts. So attribute, you are already familiar with. The attributes are the various characteristics of the dimension. Like in location dimension, the attributes can be state, country, zip code, etc. So dimension table contain attributes. Fact table is a primary table in the dimension model. So fact table contains measurement facts and foreign key from the dimension table. So dimension table contains dimensions of a fact. They are joined to fact table via a foreign key. So dimension tables are denormalized tables. Fine, they are denormalized tables, and dimension attributes are the various columns in the dimension table. I will show you dimension model in the next slides, and these points will become clear to you. Dimensions offer descriptive characteristics of the facts. So dimensions basically have hierarchy. Like this, if you are talking about item is a dimension. It has hierarchy, that it has there can be various categories and subcategories inside it. So basically, the scene maker wants to see things in hierarchy, like he wants to see item wise detail and sub category wise detail. So that's why dimension. The schemas in data warehouse. Schema is a logical description of the entire database. So it includes the name and description of records of all record types, including all associated data items and aggregates. So all these things are included in the schema. So first is the stars. There are three types of schemas which we use in the data warehouse. First is the star schema, which is the most simpler one. So each dimension in the star schema is represented with only one dimension tables. Basically, the dimension table in star schema are denormalized, which that's why it has fewer join operations. So this dimension table contains the set of attributes. All the set of attributes related to that dimension will be in one dimension table. And there is a fact table at the center of the schema. It contains the keys to each of the dimension tables. And the fact table also contains the attributes names, dollars sold and units sold. So besides the keys, there are facts in the fact table, like dollar sold, unit sold. So this is the representation of the star schema, which is the most significant in data warehouse. So these are the dimension tables: time, branch, location, and item. And the dimension tables are denormalized, means all attributes related to time will be in one dimension table, and all attributes related to branch will be in one dimension table. And dimension table also has a primary key, that is for example in time table there is a primary key time underscore key, which is a foreign key in the fact table. So you can see that there is only one kind of relationship between these tables, and that is one to many relationship between the dimension and the fact table. So there is one to many relationship between the dimension and the fact table, and these are in dimension tables are joined to fact table via means a primary key foreign key relationship, and these are the keys which come from various from attached dimension tables, and these are the facts, numerical measurements of the business. So basically facts are numeric attributes. So these keys can also be numeric, but uh, facts are those numeric attributes that are non-key. So the key attributes, if numeric, can't be fact. Fine. So Facts are non-key numeric attributes. So, for example, dollar sold and unit sold. So, as if you compare, there is as compared to ER model, this schema is very simple. Means there are only two kinds of relationship and two kinds of tables having only one kind of relationship between them. So if there is any change in the business, you just have to add one, for example, dimension table or any attribute inside existing dimension table. So it is simplified. This is another representation of star schema. It looks like star. These are the facts. Facts are the numeric attributes that are non-key. Features of star schema. So dimension hierarchies are collapsed into single table for each dimension, and this results loss of information. For example, this can be, you can say, a disadvantage of star schema, uh, that now the hierarchical information is lost in, because there is only one dimension table for one dimension. So now this information is lost, that which attribute is the subset of which attribute, like under year month comes. So this attribute is up in the hierarchy, and this attribute is, yeah, or for example, quarter comes. So this attribute must be up in the hierarchy and this is down in the hierarchy. So this information, by just looking towards the schema, you can't tell that which is the subset, which attribute is the subset. So this hierarchical information is lost. So a single fact table created with a single header from the detail records results in simplified physical data model, and it has fewer tables as compared to ER model, and as a result there are fewer joins because there is only one type of relationship. So there are automatic SQL generators as well. So if you provide such schema to automatic SQL generators, it becomes easy for that tool to generate SQL against that. So it results in high performance, some requirements of additional space. So next is the Snowflake schema. This is another type of schema. So in what is the change here? In this, some dimension tables are normalized. In the star schema, the dimension tables are denormalized. While if some dimension tables are normalized, we can call it Snowflake schema. So the normalization splits up the data into additional tables. Obviously, as a result of normalization, additional tables are added. So unlike star schema, the dimension table in Snowflake schemas are normalized. For example, the item dimension table in the star schema is normalized and split into two dimension tables like item and supplier table. For example, in star schema, if item dimension is represented by one table, then in Snowflake schema, it can be represented by normalized item and supplier table, two tables. So this is representation of Snowflake schema. As you can see that some dimensions are normalized. Now the hierarchical, you can by just looking towards the schema, you can have some information about the hierarchy as well. So the difference between the two schemas, uh, star schema has denormalized dimension tables, and it, as a result, it results in fast query performance. And in this, some dimension tables can be normalized, and high level of data redundancy, because the dimension tables are denormalized, so that's why redundancy can be there, and it has, as compared to star schema, it has low level of redundancy. So single join creates the relationship between the fact table and dimension tables, because there is only one kind of relationship and only two types of tables. So a single join creates the relationship. So it requires many joins to fetch the data, because now the number of tables are increased in this schema. So if you want to retrieve information from multiple tables, so you may require join. So it is simple as compared to this. So in this, the hierarchies are collapsed, as I told you before, that all the attributes related to one dimension will be in one dimension table. And here the hierarchical information becomes visible. So last one is the fact constellation schema. So the difference is it has multiple fact tables that share dimension tables. Now in star schema there is one central fact table, while in fact constellation schema there can be multiple fact tables. So it is also called galaxy schema. It is complex because it has multiple fact tables. So if you want to model uh, a schema of a very complex problem, so then you can use this type of schema, fact constellation schema. It is difficult to manage as it is complex. So next is the following diagram shows two tables, namely sales and shipping. The sales fact table is same as that in the star schema. There is now in the next diagram, there are two fact tables. One is the sales fact table and other is the shipping fact table. And shipping fact table has five dimensions, namely item key, time key. These are the dimensions of the shipping fact table. So this is the fact constellation schema. You can see that this is the sales fact table and this is the shipping fact table, and it has multi-part keys. So these are the keys of the shipping fact table. Like it is attached with item table, time table, location, shipper. So it is attached with multiple dimension tables. So basically, fact tables share dimension tables in this fact constellation schema. So benefits of dimension modeling, uh, it as we discussed, uh, also it improved data retrieval. So optimized for data retrieval. So it is a simplified model for business reporting. So it through this schema you can get fast aggregates easily. The simpler queries dimension model can result in improved performance for aggregation operations. We can get fast aggregates using this schema, and it is simpler. That's why it has better understanding. By just looking towards the schema, you can have a better understanding about the business. So it is extensible. For example, if there is any change in the business, that can be accommodated easily in this schema. So that's all about dimension model.